Welcome to Information Service Engineering. This is lecture number 2, Natural Language Processing, Part 2. This is Part 2 of the second lecture, and we will talk today about so-called finite state transducers, which are a special kind of finite state automatons that we have already talked about in the last part of the lecture. So, as you might know, finite state automata can recognize, which means they can accept a kind of string, which is of course necessary if we want to analyze, for example, the morphological structure of a word. But what they don't tell us is what exactly is the internal structure of the word. We can accept the word if it's formed correctly, but we don't know anything about, how it is constituted. And this is something we want to know. We want to know about the internal structure of that word. What we need, therefore, is not only a finite state automaton. What we need is some kind of a machine that maps the input string to an output string that encodes this internal structure. And then this is a so-called transducer. So what we read, the input, is the so-called surface form. So we read, for example, the word cats. And what we want to get as an output is we want to see that cat is the stem and that this is a noun and cats was the plural form. So this is what we want to have. We want to have the exact lexical form, the morphological analysis of the input string. That this is constituted as a noun and it's its plural form. Okay, how do we achieve that? We achieve that by extending the model of the finite state automaton to a so-called finite state transducer, FST. The only difference here is now that instead of a single input string, this kind of finite state automaton has a two-tape input tape, which means you have two lines of inputs and one of them can also be read as an output. So you need two tapes. As you see here, you have two different symbols on each arc and they are separated by a colon, which means the first one, the left one, is tape number 1. The second one, the right one, is tape number 2, exactly. So let's have a look at the formal definition of this FST before we go into the application. The application will be much easier, so don't get confused about this, let's say, complicated formal definition. We extend now simply our already existing definition in the following way, that we define a finite state transducer T, which now consists of an even larger tuple. And the tuple again consists of a finite set of states that we have, and of course we have the finite set of input symbols. This is all the same, but now we also have a set of output symbols. This is capital delta. It's a finite set of output symbols. Then we have the designated starting state or initial state Q sub 0. We have the set of final states F. We have the transition function delta. Here already we have the transition function in the form of a non-deterministic finite state automaton. We have talked about the difference, deterministic and non-deterministic. The non-deterministics, just to recall that, they also include the so-called epsilon transitions, which means they can change the state without considering any input symbol. And then we have a second function which is the output function, and this function is called sigma. Sigma is the output function, and sigma maps also the set of states Q together with a set of states of input symbols sigma 2, and now any kind of potential subset of the output symbol set. So delta of Qi then follows in omega, which is then element of sigma star, which is the set of all possible strings which can be constructed based on the set of output symbols. Okay, so what this finite state transducer does is it creates a relation between two kinds of regular languages, the input language and the output language. Just consider input language and output language in the following way for exactly our problem we are considering now. We have an input language which has English words like cat, cats, fox, and foxes. And our output language should be in the following way. It should say for cat, this is a noun and it's singular. For cats, it should say this is cat, it's a noun, it's plural. For fox, this is fox, a noun, singular, and foxes, fox, noun, plural. And exactly this relation should be constituted, that cat and cat, noun, singular, belong together. So you see here the transducer T defines a relation of languages, L in and L out, language input and language output. And here cat and cat, noun, singular, comes together in one tuple. And then we have cats and cat, noun, plural, come together, and so on and so on. So exactly this relation will be represented with the help of a finite state transducer. This is exactly what we want to do with it. You can use these finite state transducers in NLP for several applications. For example, you can use it as a recognizer, so it can recognize a pair of strings and can accept or reject them. Also, it can be used as a generator, so the output, or it can output a pair of strings for a language. Or then it comes more interesting, it can work as a translator, so it reads a string and outputs another string. And this, for example, is exactly what we want to do. For morphological parsing, we read letters as an input, and the output will be the morphemes and, of course, the purpose of the morphemes. And you can also more generally use a finite state transducer as a kind of relator, which means it computes a relation between two different kind of sets, which are represented by the input language and the output language. But we want to use the FST as a translator, and especially for the case of morphological parsing. So let's have a look how FSTs can be used for morphological parsing. As we already said, we have two tapes. So we have the upper tape, which is the lexical tape, and we have the lower tape, which is the surface tape. The surface tape is the input tape, so it contains the input alphabet and it reads letters. And there, for example, we can read the surface form cats. The upper tape is the so-called lexical tape, and there in the lexical tape, our output should be the stem of the word we have read, which is cat. And then, of course, it's morphological analysis, so cat is a noun, and of course cats here was plural. So exactly you see here in the lexical tape what we expect to be the output of this input. Okay, so for morphological parsing, for example, you have then to consider graphs like this. And here, for example, if you consider goose and geese, you see here, for example, that you always have pairs in the input and output, which are either so-called default pairs, which means a G is mapped to a G in the output, or you have so-called feasible pairs where the letter changes in the output. Let's read that graph that we see here, for example, and to do that, we introduce two new signs. So for example, we have also to indicate what's the boundary of a morpheme, and we do this with an hat. And also we indicate what's the boundary of a word, and we do this with the help of a hash sign. Okay, let's have a look at the graph. We start at the initial state 0 here, and then let's have a look first at the uppermost path. In the uppermost path, we have as an input, the input always is written below the path. So we have an F, which becomes an F in the output. We have an O, which becomes an O in the output. We have an X, which becomes an X in the output. And then we come to state number 5. State number 5 then has an epsilon transition, which tells us as output, this is a noun. So the output in the lexical tape will be plus n. The next thing then is, for example, if, let's take the upper path, this was the end of a morpheme, and now we have on the input tape an S, and then we have a word boundary, then this states, okay, this is a plural, so we output plus PL, which means plural. On the other hand, if next thing on the input tape is the word boundary, the hash sign, then this is singular, and we output singular, and we end in state number 7, which is the end state or the accepting state. So you see what we do here. For example, if we read fox, the output then will be fox, it's a noun, and it's singular. If we read foxes, it's fox is a noun, and then simply because we read the S after the morpheme and we have the word boundary, then we say this is plural. Now you will say, fox, there does not simply follow an S, there follows ES. Yes, this is an orthographic rule we will take into account separately. So this is not the full story. This is only to see how this relation of lexical tape and surface tape really works. What we need to make it, let's say, really work is we need an intermediate representation. We need a third kind of tape. You will see how this works. So sometimes English requires spelling changes exactly at morpheme boundaries. We have already seen this for the plural S, for example, but also in other cases we have exactly these spelling changes. And these spelling changes, they have to be introduced via so-called orthographic rules. We have a few examples here. First, we consider consonant doubling. For example, if you end in ing or ed after a verb, then, for example, the consonant at the end of the verb will be doubled. So beg becomes begging, while begging has a double G. On the other hand, often also an E, which is at the end of a verb, will be deleted. So the silent E will be dropped before you have the continuous form with ing, or you have the past tense with ed. So make becomes making, and the silent E at the end of make will be dropped. On the other hand, you also have for certain nouns an E insertion. So E is added after consonants like S, Z, X, or C, or G, or SH, or also before S. So fox becomes foxes. You do not simply add an S for the plural S. Then what you also do, you have a replacement of Y. This is what we have already seen for the plural of city becomes cities, so Y becomes IE. And what you also have, for example, you have the insertion of a K. If a verb ends with a vowel and a C, then C will be CK. So panic, to panic, if you then do the past tense panicked, you have to add a K. So these are certain orthographic rules. These are not all the rules that exist, but they also, of course, have to be considered in our finite state transducer if we want to do morphological analysis, which makes this process much more complicated. So let's have here an example with the English plural S. For cat, it's quite simple. We simply add the S, we have cats. For dog, we simply add the S, we have dogs. But if we have fox, then it becomes foxes in the plural. If we have bus, then in the plural it becomes buses. To be able to deal with these kind of orthographic rules, we need something like a third tape, which means we need an intermediate representation which captures exactly these morpheme boundaries, where exactly these changes happens, and also the word boundaries. So let's have a look at these three kind of tapes we are dealing with, or three kinds of strings. So first of all, it's the lower one. We deal with the surface string, cats and foxes. And they have to be in with the first transducer to be translated into cat, followed by a morpheme boundary, followed by a plural S, followed by a word boundary. Or foxes, exactly the same, has to be in the intermediate representation, be translated via an FST into fox, followed by a morpheme boundary, followed by a plural S, followed by a word boundary. And now starting from that intermediate representation, the second transducer that we use here simply transforms cat, morpheme boundary, plural S, and word boundary into the lexical form, which is cat, so this is the stem, which is a noun, which is in plural. And the same happens with foxes. Which means, so this is a so-called intermediate to surface spelling rule that we here exactly add between the first and the second layer. So if there is a plural S, followed by a morpheme ending in X, Z or S, then insert an E. So this is an orthographic rule that we here establish between the lower and the intermediate representation form. So what happens here is, you see it here again, illustrated with the tapes. You have a first set of transducers which translates between the surface forms and the intermediate forms, the according intermediate forms. And then you have a lexical finite state transducer which simply translates between the intermediate form and the lexical form. So to be able to do a full-fledged orthographic analysis, what you need is a set of finite state transducers simply substituting with the help of orthographic rules the surface forms into an intermediate representation. And then you need one so-called lexicon finite state transducer which translates the intermediate translations or intermediate representations of all the words into their lexical representations. And there you have the entire morphological analysis. And this is how, based on finite state transducers, which are finite state automata, a full-fledged morphological analysis in natural language processing can be implemented. You see, it's not so difficult. The interesting thing is that exactly this kind of technique, these finite state transducers, can also be applied, for example, to implement a stemmer. The most prominent stemmer probably is the Porter stemmer. This is rather popular, and this is used for information retrieval. For example, it's used to convert strings and words that are encountered in a web page into its stem form because they are taken into the index of a search engine, for example. And it's also used for text categorization tasks. And it works based on a series of simple cascading rules, and it's able to detect, for example, also rather complicated changes. So, for example, if you have the ending ational, so like in relational, it can find the stem form relate. So ational will be substituted by 8, or ing will be substituted by nothing, which is an epsilon. So motoring, the stem form is motor. So lots of these kind of irregular forms can be immediately also encoded with the help of the Porter stemmer, or grasses will be substituted, SSES will be substituted with SS. So this is a stemmer, and this can simply be implemented with the help of a finite state transducer. The only problem is it also commits many errors, so organization will be, with the help of these rules, stamped to organ, or doing will be stamped to do, and policy will be stamped to police, which is not correct. So there are lots of irregularities which have to be taken care of afterwards. But for a large percentage of words, the Porter stemmer works perfectly fine, and for information retrieval purposes, it works sufficiently fine. So you can try it out. There is a link to one implementation of the Porter stemmer. Another prominent example, what can be done with finite state transducers, are chatbots. You probably are familiar with chatbots, and one of the very first chatbots and the most famous chatbot is the so-called ELIZA chatbot. ELIZA was implemented by Weizenbaum, very famous computer scientist working in artificial intelligence, and he used these kind of finite state transducers to implement a chatbot that pretended to be a human psychiatrist. So if you read that dialogue here, the computer says, "Tell me more about your family," and then the human says, "My mother takes care of me," and then the computer asks, "Who else in your family takes care of you?" and so on and so on. So always referring to the last question of the patient and acting like a psychiatrist. Many people who were dealing with that program in the 1970s were really thinking, this is a human psychologist talking to me. So this was really amazing. And you see here on the next slide how you can, for example, establish a dialogue like that based on FSTs. So for example, if the human says, "You don't argue with me," and the computer would answer then, "Why do you think I don't argue with you?" It's rather simple. So if a sentence starts with "you," then simply I go on and I replace "you" with "I," and then I have a "me," then I replace "me" with "you." So it becomes I don't argue with you instead of you don't argue with me. And then because the computer acts like a psychiatrist, of course, we add as a prefix, why do you think? And then I don't argue with you. So it's quite simple then to come from you don't argue with me to why do you think? I don't argue with you. And this, of course, works with any kind of statement of assumption that starts with you and contains a me. You simply switch it around and then you ask, why do you think? And you have the same sentence with you and me simply switched to I and you. And if you do it cleverly like ELIZA, it mimics a human psychiatrist. Okay, so this was the very first part of analysis in natural language processing. In the next part of the lecture, you will learn more about statistics and about language models based on so-called n-grams.